Okay, so the first one, it is basically a latch. So how do we say it is a flip flop or latch? Because see the way we do the things in industry, right? So this is basically a kind of identification for the registers, basically flip flops. Okay, so this is basically a positive level, positive edge triggered, and this is a negative edge triggered flip flop. Whereas this is negative, it's basically positive level sensitive. Okay, so this is basically a latch. And now if it is a negative latch, it is going to be say something like this. Okay, it is something like this. Okay, now so how the latch would behave? So latch would behave during the passage on the positive level. It is going to be kind of a transparent. Okay, during the positive edge, the latch is going to be transparent. Now in this case, it is a positive, level sensitive. Okay, now what does this meaning is it is going to be say kind of like this. Now it is just that you have to extend it like this. Okay, now this is clock and this is your D. So what we would do is we would actually copy whatever is there in this period as it is, and then it is kind of just follow this. Okay, now leave this part at this point of time. Again, come over here. It is kind of just say this. Whatever is there in that time period, it is going to be kind of like this. Now you have to just extend this as it is. So whatever the value at the last, that would be retained all the way till the next edge. Okay, so this is how it is going to be in case of say latch. Say this is going to be q, say latch, latch. Okay, is it clear? And now when it comes to registers for flip flops, okay, what is it going to be? It is going to be kind of say only on the edge, positive edge, whatever the value is. Say this is positive edge triggered flip flop. Now at that point of time, it is kind of say one. Okay, say this is one. Okay, now here it is 0, so that means it is going to go all the way till this particular thing, and then it is going to go to 0, and then it is going to continue. Okay, this is going to be q, say b, it is going to be say b, and say this is a. Okay, and what about this one, the third one, say QC, which is what is this? It's basically negative edge triggered flop, negative edge triggered flip flop. Now, sometimes people say, like, kind of, Kumar, can I draw this and invert it? Can I invert this? That would become a kind of negative edge trigger. So people used to ask me something like that. Okay, but just remember that no, that is not the way. So some people have done this way. Yeah, this is exactly opposite, negative is triggered, right? So something like this, but this is totally wrong. So you are not supposed to do this, where you have to, look at the edge exactly the way how it is actually, kind of treating, how the data is getting captured. Okay. Now QC, which is going to be negative edge triggered register. Now, if you look at here, you need to look at the negative edge triggered. That is a kind of thing where, so it is 0 here, and then here it is 1, so that means it is going to be kind of say 0. Now here it is going to say kind of go up, sorry, it is going to go continuously, it is going to go 0, continue all the way till here, and then the last portion it is going to increase. So this is how your timing diagram says. Basically, your clock and D was given. Now, when you have to draw output waveform, so this is how you have to draw it. So, can someone quickly summarize what we learned here? Can someone summarize quickly what we learned here? What is the, how do you draw the output if it is a positive level sensitive device?
Yeah. Yeah. Let me explain. Hello, sir. Can you hear me?
Yes, yes, I can hear you.
Yeah. First, in latch is generally level triggered. From positive latch, uh, from
Okay,
positive
one
clock,
minute.
we want to follow.
1 minute, 1 minute. So it is not a level triggered, it is a level sensitive.
Yeah, level sensitive. Sorry,
Yeah.
level sensitive. For positive latch, we want to follow at positive level. The same data will obtain. At negative, oh, it will not obtain for positive latch. Vice versa to negative latch. Uh, in flip flop, edge triggered from at positive edge triggered, we want to see the mm, present value of the data at 0 or 1, at which point it's starting. Based on that, we want to continue that. It will not obtain the same data what we given. That edge triggered alone it will follow. Negative flip flop, vice versa.
Okay. Okay, all right. So on a simple note, latch is basically a level sensitive, and during the sensitive, say if it is a positive, then or during the positive level, it is a transparent. You can use that word transparent, as simple as that. Okay. And when it comes to flip flops, it is edge triggered, and whatever the value at the time of the edge, rising edge or falling edge, and that value would be considered. Okay. Okay, all right.
Yeah, 1 second.
Yeah, go ahead.
So the QA what you have actually Q latch, right?
No.
So QA bar is nothing but inverted of Q latch, is it?
Yeah,
Or
right.
that works at the like
No, no,
negative
this,
edge.
no, 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 that's not negative edge. It is just opposite of this. Whatever you say,
Okay.
no, it is just opposite of this.
So inversion of whatever it is.
Yeah, right.
So irrespective of any clock cycle. Okay.
Yeah, right. And let me tell you,
Okay.
see, in industry, right, first of all, you will not have a flop with both of this output. You will have either Q
Yeah, yeah,
or
correct, correct.
Q is bar only. So you will not have a both. So this
Okay.
for the people who are kind of yet to see the designs, right? So only thing that you would see here is you will see either only one output pin. It would be either Q or Q bar. Okay. So
Okay.
now I can actually show you guys how what are the different flip flops. So you might be seeing okay a simple D flip flop or something here, but the way in industry we have is it's completely different.
Okay. So when people ask us to actually say for instance for actually D latch, so if they ask us actually only to write QA bar, okay, so
Hmm.
we have to check the positive edge of the latch and then like we have to do not the like negative based on the QA bar output,
See,
right?
if you ask me, it is going to be kind of, see,
Inversion of whatever it is there.
this is going to be QA bar. Okay, that's all. So it is just like that. You can just add a kind of, a simple inverter here.
Yeah, yeah, got it. Okay.
That's the basic.
Okay. Yeah.
Yeah.
Thanks for.
Anyone else has any other questions?
Sir, can I ask one
Go
question?
ahead, go ahead.
What is the purpose of this? Where we use this leaf flip flops?
That is the D flip flops are the one that is used heavily in industry. Okay.
In future class, we will understand. Sir.
No, your voice is there is a lot of noise in the background. What is it? So I'm telling you, the DFF is the only flip flop that we would be using in our designs. I'm just showing you. Say, for
What?
example,
What?
now assuming, see, we have a USB top is one of the design. Say now you go inside, you will have your, the Verilog, net list. Okay. Now, if you see in this, say you will have a DFFs only. You see here. There is no other flip-flops you will ever see in any of these things. Okay, so you have a DFFs only. All the registers that we have is basically something like a DFF. We don't, I know that, we have a SR flip-flop, JK flip-flop, and, different flip-flops, but we don't use any other flip-flops. We use only the data flip-flop and the D latch. Okay. Now, even now, if you guys look at our library, okay, okay, now you look at here, how many different flip-flops that we have. Is that screen visible?
Okay, sir.
Yes, we can see.
Okay, so if you look at, right, like you will not see any other JK flip flop or any of the other things because, okay, let me just see. Only I just grep using only a flip flop, FF. Okay, now you have 100 plus things are there. Now look at here, see DFFs, DFF, and then see what is this meaning of NAR. These are all some things like kind of where you have a negative and then some will have only, so in the registers, if you look at, there will be a set and reset registers. Okay, see you have a set, okay, and you have a reset, okay, and this is your clock, and say Q and then D, okay, and all these things, okay. Now, these are all the basic things. See here, RDFF. Now, these, so ideally speaking, you will see only DFF present in your library. So, we will not be having any SR flip flop or JK flip flops in the design at all. Only a simple D flip flop, you will have it in your libraries. Okay, you guys can see it, and pretty much we use SDFFs in our design. So I'm not sure if I gave this as a homework. So what is this SDFF? And I want you to explain SDFF in detail, say off page. That's your assignment. Okay, it's basically called scannable D flip flop. So what is the difference between DFF and SDFF? That's your assignment question. So DFF versus SDFF. That's your assignment questions. I want you to draw a simple schematic like this and how the SDFF is built and things like that. I don't need your in-depth of CMOS circuit that we will do in upcoming classes. But today I just want you to go and understand. So which one we use in our design? So pretty much we use DFF, but then what is that SDFF? Okay, that is simple. It's called scannable D flip flop. So if you see here, these are all your cell types. Okay. Now, in case if you wanted to know more on it, so you will have always the library document. So these are all the cells that are actually, see, okay, you got it here. Okay, see here, D flip flops. Now, what are all the different types of flip flops that usually it will be in your library? Or basically, one is say Passage DFF. It's just simple DFF X1, X2, and etc. Now, with asynchronous low active set. AS meaning asynchronous, I mean async low active. Okay. Now this is asynchronous low active reset. So the tool, when we do synthesis, the tool actually picks whatever that it feels the right thing. Okay, because that all these things are coded in your RTL. Okay, now if you look at here, you want only a simple regular flip flop without set and reset. You can actually pick DFF. Okay, just simple DFF. Now you want only set, you don't need reset, then you can actually pick this flop. The tool could actually pick this during synthesis, and these are all kind of defined in your RTL. Okay, and say this low active set and reset. Say you need a register or flip flop with both set and reset. Okay, then you, the tool would actually, or you should use this particular register. Okay, now this is synchronous low active. So here it is asynchronous low active, whereas this is synchronous low active. Okay, so there are different things. Now you see here, this is negative edge triggered, DFF. So DFF N X1. That's what I was just telling. It's a negative. So you have all the kind of registers given to you in the standard cell library, and these would be used when we actually do a synthesis. Now, how this is going to be picked, or who, on what basis this would be picked. Now, if you look at your RTLs, so they will have, always at something. Okay. Now, if you look at your design part, okay. Now, if you guys look at this, is your RTL, where this actually developed by designers. Okay, not neither you nor me. Okay, so we don't work on this. So it was developed by the front end designers. You know what? Now they actually have something like this. Say always at passage clock. Now they have got a reset. Okay, now this is how. Say if they don't have this reset signal, then you don't need that flop with reset. Now, in this case, you have got a reset signal where the moment reset is active, all your outputs are going to be 0. So now in this case, what is that it would actually pick? It could actually pick something with reset enabled. So it could be picking, DFF AR or DFF SR. Okay, got it. So the RTL guys would decide what is that they want. Okay, here I don't see a set here, it is only a reset. Okay, so simple. This is actually a reset. Only reset is needed, we don't need set. So when you do synthesis, this particular RTL would actually use only the registers with reset, positive reset or a negative reset. It depends on the signal how it is actually picked. Okay, now look at here, there are different, so passage registers and negate registers and all of this. Okay, and you see here, we are actually talking about only Q out and Q in out. So we will not have both Q and Q bar in any of the registers. Okay, so you see here in this case, only Q out. Okay, and here only Q in out. Okay, we will not have both Q and Qn bar. Basically Q and Qn. Now that is on your regular flops. Now look at here, scan D flip flops. So these are all some things where your regular registers would be treated as a scan as well. So this is basically a wrapper. Okay, so when you learn something about scannable flops, you would get to know more of it. Okay, so same scan passage and scan negate everything. Okay, and then you have got a latch. See, there is a latch. So these are latches. You have RS NAND latch. So this is something like, so, but we normally don't prefer some those kind of things, where we would actually prefer regular latches, high active latch and all this. So you might want to pick any of this. Okay, so the first thing that when you start working on a project, you should understand what are all the cells that are there in your libraries. Okay, so each and every design, or when you work on something, there would be a library document that could have been given to you, and you should always refer this and understand, okay, what are the different cell families that are available for you. Okay, now say simple here, there is something called a clock gate. Now say there is a different clock gates, say passage control, luggage control, and so these are all your clock gates. And then delay flop, delay registers, not registers, combinational delay. Okay, so it is something to fix the hold. So we have something called hold analysis that you will get to know when we do static timing analysis. So the signal might be traveling faster. So if you want to reduce that, or slow down that signal, you can actually use these cells, which could actually add more delay. Okay, so we always should prefer, the first thing that I always suggest you guys is, the moment you start working on any of the designs, understand the technology and understand the libraries. Those two are the basic things that I always suggest. Okay, now say there are some more things. So retention flops. So yes, scan, retention, D flip flops. Okay, you see here, save and restore pins. So there may be a different thing. So I'm telling you, if you ask me, Kumar, do you know all these cells? I may not know, but I know where to look for such informations. Okay, so what is this flop is all about? And I know, I need to go and refer the library document, which could give me more details. Okay, so any questions here?
Can
So
I
your
ask a
previous,
question?
yeah, go ahead, Mas.
Go ahead, Mustafa.
My question is, can you show the script RTL design which you showed before?
Okay,
You art.
yeah, right.
Is this RTL is synthesis design or not synthesis design?
No, this is not it synthesized. This is just a pure RTL, and if you want to see
Mhm.
a synthesized one, I can show you.
When we are designing, we should synthesize, right?
Yeah, ideally that has to be synthesized. So I
Uh,
do have the design in a synthesized one. You can actually see this. So this is basically what module it is. RX. Okay. So okay, you see here, this is the kind of synthesized net list. This is the the RTL, which is before
mhm.
synthesis, and now this RTL went through the synthesis part, and then I have actually this is the part of code. This is the code that is actually, you see here. So these are all something.
Yes, all these are which you showed before, right? The document, PDF document, for example, line number 845.
I
Please can you show the code, please?
Which one?
Script, show code, the synthesis design.
Okay.
For example, 849
Okay.
TFFX,
Right.
right? It's the refer to this document, right? RVT is the
Yeah, it is all same. So DFF X1 is basically, it is a part of the same library part.
in the document. Yes, the cell name, right?
Yeah, right.
In here.
Yeah, 1 minute.
Okay.
Let me just show you
Okay.
here.
Okay.
I can just show you. Just give me a minute. So passage DFF with both Q and QAN outputs. That's what this I could see that. You see here DFF X1. Okay. Now
Hmm.
let me just, yeah. So this is the uh, register, that is DFFX1, that is being used. Now the way it is kind of having both Q and QN bar. Now only if you want only Q out, so your tool might be able to pick something like this. So these are all purely depends on the way how it is coded. Now go ahead, Mustafa. What is your question?
Yes, I understand. But this was my question. I understand.
Okay.
I understand. Thank you.
Okay. There was some other question.
Yes, Kumar. Yeah. So like, I was just asking. So as per the RTL design, like we'll come to know what is the flop we have to use, but the drive strength and all that will be decided based on.
Your timing
So because we
requirement.
have X1, okay, timing requirement.
Yeah,
Okay.
timing and area. So there are, see the drive strength, we are yet to cover all this. So we will be covering
Okay. Okay.
complete standard cell
Uh-huh.
libraries part. Okay. So
Got it. Got it.
where I would
Yeah.
be talking about, so when we say it's library, so these are all the different, variants or basically models that I call it. So it is like kind of you have a
Okay.
.lib or .db and then .v and then CDL and spice and then GDS and then ref, the lef and then FRAM views and then all these are all your standard cell models. So we would be looking at all these in the upcoming classes.
Okay.
So now coming to your question, so we have actually talked about the drive strength part. That would be kind of depending on your the timing requirements and area requirements. So uh, the tool might pick.
So and then the device type also HVT, RVT,
Exactly.
ULVT. So
Every
that is also based on area or based on any
leakage.
particular VT number. Okay.
No. So your VT flavors would be chosen based on your timing and leakage power requirements.
Okay. Okay. So that will be part of RTL again, or is that part of synthesis?
No. So RTL will not have any information about it. It is just a
Okay.
purely any kind of programming language that we have. So it's simple like this.
Okay.
There will not be anything.
Okay. Yeah, got it. Yeah, that is why. Okay.
Okay. But
So then how does the tool picks from
so
where
that
it
is
will
actually
understand?
no. That is all I can explain you when we cover synthesis part.
Okay. Okay. Yeah, sure. Okay. Yeah,
Okay.
sorry.
So, say on a simple note, I can just give you a quick intro of synthesis. So now, so what is synthesis? Okay. See, I've got a kind of read RTL. That is a first step, and then analyze. Okay, and then elaborate. Okay, and then generic generic synthesis, and then syn map. Okay, and then say we call it like syn opt. So these are all the sub steps that actually happens during the synthesis part. Now what is the first part will do? It will read this RTL as it is. Okay, it just reads RTL and then it checks syntax. Okay, there may be some syntax issues. So if for example you missed some things or you have forgot to define some things and all that, so it checks syntax and then elaborate is something. See here you have got a bits that are kind of 0 to 15 or a 16 bit and all that, so it would actually try to elaborate each and every bits and then it checks everything is linking properly or not. So that is a elaborate. And then your design is now, this code is now converted into a simple OR gate and AND gate, things like this. So this is without any library. So generic synthesis is something general form of gates. It will not look at what is the standard cells that are available in your library and also your standard cells comes into picture only at this position, this part. Okay, now once the generic synthesis is done, then now your synth map, that is basically mapping to your library. So now here, how many inputs there here? What is the cells? This is simple cell. It is a kind of OR gate, two input, as simple as that. That is a basic thing. Now, when you run synth map, okay. Now, what are all the different cells are there in your OR? Okay, see if I have to ask you this. Okay, see now if I have to now grab a simple, let's take it NOR, okay, for our, okay, now, so grep minus b, x NOR I don't want, and then let's see, grep, okay. Now, if you see here, there are, two input NOR gate, okay, and then say this is NOR gate. Now two input NOR gate. Now see it has got only here HVT, but what and all we read it. So we might read HVT library, SVT library, LVT library. Now looking at the two inputs, so you will have both of these things together, say kind of NOR 2 x0 x1 x2 x4, okay, and then say you have HVT and SVT which is available for our for the tool to use. So now the tool would pick either x0 x1 or HVT or SVT, any of that, and then it will map it to that particular cell. So it is going to be kind of NOR 2x2 underscore HVT. Now this is what we call it, like kind of the mapping. So generic gate, during the generic synthesis, it just knows only the NOR gate. It doesn't know what is a cell that is present in library. It is not mapped. So now during the syn map, that NOR gate is kind of now mapped. Picked the cell from your library. This is, remember this is the step where it become tech dependent, technology dependent. Your libraries and what cells that are present in your standard cell library, all this matters from this point only. Syn map. Okay, now first step is to map the cells, all the generic gates to standard cell cells, and then your syn opt. Okay, so then after that, it would actually try to optimize your timing. Okay, so it is basically a PPA optimization, power, performance, and then area, all that it would be optimizing. So end of the day, your mapping actually happens from your libraries. I mean, all the cells would be whatever the cells that are defined. The tool would pick the right cell depending on mapping time. It just picks it randomly normally, but during the optimization, it could actually upsize from x0 to x2 or HVT to SVT and all that. Okay, that is what actually happens in synthesis. Okay.
Thanks a lot, Kumar. Yeah, so it is nice. So all these details, like, yeah, until you explained, we didn't know, but now it is more clear.
Okay, anyone has any other questions?
Just like another question, like this like synthesis work is done by DFT people, is it?
No, there is separate synthesis team. DFT is separate.
Okay, okay. DFT separate. Okay, okay. Yeah. Okay.
DFT is separate. So we do synthesis and then we give it to DFT team.
Uh-huh. Okay, okay. Got it.
Okay. Okay, moving on to the next topic, which is registers. What is the registers? Okay, so before we go and look at registers, let's try to understand what is meaning of excitation table. What is this excitation table? Remember, so you have got different flip flops, right? So SR and then D, JK and then T, right? Now, when we design a circuit, this excitation table is the one which is we refer it to design the circuit. It's basically, say for example, now you may see something like this. So this is something that we call this as a combo logic, combinational logic. Okay, it's people call it T combo or combo logic, you know, combo delay and all the different naming conventions. But just that your what do you call it's kind of rich to rich circuit that we call it. Now based on this excitation table only, say it's simple, like this is your current state, okay, and this is going to be the next output. This is what your next output that you are expecting it to come. Now this is supposed to be your input, Okay, so this is your current output state, and this is going to be your next output state. That is what you are expecting next after one pulse, after one clock pulse. This is what you are expecting. Now, what is that you have to give to the D so that you will get this output? Now, this is nothing but your input. Okay, so now this actually helps you to come up with the logic that you wanted, so that you get the output, the desired output at this at this pupil. So excitation table is actually an important one, and that actually helps in designing the circuit, considering what is the next output that you are actually looking at. Okay, so we will design a counter, and then we can actually look at it. But before that, let's cover this registers part. Okay. But remember, this excitation table is one of the important things. So sometimes, people would ask in entry level questions. Okay, so people, some of you are kind of, recent passed out, and you might be, in case if you are, appearing for written test and things like that. Say sometimes they might ask, okay, they might give something like this, and then they ask whether it's true or false and things like that. So you just know that, D is basically always transparent. So this is your output that you are expecting. Your input should be exactly the same. As simple hint. Okay, but when it comes to T, this is your input. Okay, and this is your kind of the out this of current state, and this is going to be the next state. Now the way we look at is, see here it is 0 and the next state is 0. So that means you can actually give T input as 0. That means it's a memory, it retains the same thing. Okay, now when it comes to 1, say current state is 1 and your next state is also 1. Now that means that is also same memory, you don't need to do anything, you just have to stay in the same state. But now you want to change, you want to make it alternate. Now what is that you need to do is, see your current output is 0 and the next output you are looking at is basically 1. Now that means if you give T1, that will keep toggling. Say simple, right? Like kind of if this is your T flop. Okay, now if you give 1, it keeps toggling. Every cycle it keeps toggling, the output would be keep toggling. Now if it is 0, that means it retains that. Actually it's a memory, it just whatever, if it is 0 it retains 0, if it is 1 it retains that 1. Okay, so you should know how to analyze this thing. So if you ask me, look at only D flip flop and T flip flop, you would be able to easily understand. Okay, is it clear? Excitation table.
Yes, clear.
So just one question here. So because previously also like I had this question, but like I couldn't raise it. So
Okay.
the reason of using D flip flop is because it is having single input and then like output actually follows the input. Is that the only reason, or like any particular reason of using D flip flop
No, it is
compared to
easy.
any other flip flops?
No, first of all, it is transparent flip flop, which is easy for you to design, the circuit.
Correct. Okay.
As simple as that, nothing else.
Okay. So and then one input is more than sufficient because like, we have SR and JK as two inputs, right? So that is, so it takes more of area also, right? So that is
Okay.
the reason we are not going with SR and JK.
Okay.
Yeah.
Okay. Moving on to the next one. Now, registers. What is the meaning of registers? So they
To register
basically,
the data.
it basically stores the data. Okay, that is the meaning of it. Okay. Now remember this. We call a simple flip flop as a registers, and then flip flops and etc. But the term in industry that we use is always registers. Okay, so launch register, capture register, and all that. Okay. Okay, now in this you have a kind of different registers. One is basically serial in, serial out. See, one or more flops sharing the same clock signal, and they kind of have it like kind of say this is a 4-bit register, so it can actually store 4-bit values. Okay, it can actually store 4-bit values. Okay, and in this case you can actually say kind of left shift, right shift, and all that. Say in this case it is kind of say serial in and then serial out. Okay, and then you have a parallel in, serial out, and serial in, parallel out, and parallel in, parallel out, and then universal shift register. So now these universal shift register meaning it can actually load all the data together, and then depending on the control you can either left shift, right shift, make it serial in, serial out, or parallel in, parallel out, and things like that. So universal shift register is something that could actually help you. It can operate in whatever the way it wants, so you can actually have a control signals which could actually do the whole stuff. Okay, now on a simple note, let's say you have a ALU. How that ALU actually works? Okay, how this ALU would be actually working? Now look at this kind of, say for example, say there is a 4-bit bus. Say there is kind of A, and then say you have a B. So this is a kind of ALU. Okay, say output. Okay, just say O. Okay, now assuming this data is continuously changing, and now would you be able to keep calculate the value properly? If the data is properly continuously changing, now how that will actually work?
Should be registered.
So now what does that meaning is, you have to add a register. Say here it is kind of, you have to make sure you know say it this way. Say it is kind of, you have a 4-bit register. Okay, now you need to have a 4-bit register so that your data is constant and the ALE can do the whole stuff, and even the output of this would be kind of register. So now all of this, okay, all of this has to be kind of say clocked. Now this way the values, you can guarantee that the values would be consistent. Say here, during only the clock signal, whenever the clock signal comes, the data at the input gets captured, and the output, the value at the A bus remains constant, and then say the value at the B bus remains constant, and then after it performs, either you do arithmetic operations, kind of addition, subtraction, shift left, shift right, or ones complement, two's complement, and then multiplication, division, remain, calculation. So there are n number of things that you might do it. Now after that, after certain cycles, your data would be out, right? So this is how we actually kind of design any circuit. So which means you need a register to hold the data, otherwise it would continuously keep changing. Okay, now that is what we call it like kind of say you need a register to hold the data. Okay, otherwise if you don't have registers, the data would keep changing, and this calculations would continuously keep changing, and you will never get the right data. Got it? So for this purpose we use registers.
Can I ask a question?
Go ahead.
Oh, can we say that all the inputs and outputs should be registered always? Can
It
you say
is,
that?
see, it is always, on a simple note, we always prefer all the inputs and outputs we usually register it and then take it. See, now simple, right? Like kind of, if this is your full chip, okay, now, and we divide the designs into something called blocks, okay. This, we call this as a kind of partition, okay. So we call this kind of, block A, block B, and C, something like this, okay. Guys, if you're not talking, please can you go on mute? Okay, so now you have a block A, say block B, block C, and things like that. So there could be a registers when you are going out, and then there could be some registers, and then when you are taking it inside. So we always prefer, everything to be registered.
Sure. Okay.
Okay,
I got it. Okay.
yeah. And you will learn all this, on how your design structure would be. Say, for example, now you may have a design like this. Okay, now there might be a memory. Okay, so there might be a macro, there might be a memory, and there might be some registers. Now, which is more preferred? Like kind of, direct input to memory, is that preferred, or it's kind of okay, or into reg is kind of preferred. So now, then in this case, what is the next thing that you would expect the designer to do? So there are many things we will discuss when we move to the, in the upcoming classes, when we, go through all the topics. Okay, so right now I'm just trying to cover basics so that, like, you understand how these registers are used, and why do we need it. And people may not realize that, what is the meaning of register. Okay, so it is, I read in college, or the career, engineering time, but where it is being used. So now when I explain you this something, okay, yeah, now this is the reason why we have registers. So we have to hold the data from changing, very frequently, and you should allow them only when it is the right time. So that means they are clocked, right? So that's a basic thing. Okay, now if you look at here, this is kind of parallel in, parallel out. See here, one, two, three, four, 4-bit register. It is kind of parallel in and then parallel out. All of them are kind of stored. Say this is what we call it, like kind of, 4-bit register, where you just, the ALU, this inputs may be changing at some point of time, but now this Q would be kind of retained, consistent, constant. Okay, so this is something I call it like kind of parallel in, parallel out. Now there is another thing called, serial in, serial out, or something people call it like kind of, the shift registers. Now see here, a data which is kind of passed inside here, and then it is kind of, going like this. So there is no logic operation. It just, the data which is getting, say kind of 10110. After certain pulse, you will get this out. Okay, now you might ask me, why do we need this? Where do we use this? So just ideally, if you ask me this, just area wastage, I would say, because it's not doing any operation, right? It's just, same data which is kind of coming here, and it just couple of pulse, it is just getting wasted, and then you're using that same data. But now remember, this shift registers, okay, this shift registers are actually used very much in our design cycle for testing purpose. It is called scan shift. Okay, this is something you will get to know when we talk about different modes of operation. So there is a testing mode, so there is a func mode, and then there is a test mode and all that. Now whereas, so the moment you go for manufacturing, right, your DFT parts comes into picture, right? So what is the guarantee that your Q is not tied to logic 1, or say tied to logic 0? So your circuit has to work, right? So during the manufacturing, IC manufacturing, there are chances that we have something called manufacturing faults. Now we need to ensure that all the registers are working fine. Now how do we test it? With the help of, so there is a testing mode which is called a scan shift. So that means it would be a kind of serially we shifting the data. Now simple, right? So you give 0 1 1 0. Now this guy gives 1 1 1 1. Now, so Will this chip work? Will this chip work? This is your input data, but your output is always 111. So will this chip work?
No.
No,
No.
there is some structural defect in the chip.
So
No.
there is something called some manufacturing fault. Okay, manufacturing fault that actually happened. That is something people call it stuck at zero, stuck at one, or stuck at zero. So it could be one of this. So in this case, likely stuck at one. So you need to test it. So that's basically this chip is dead. But now, where it is getting, create, where is the problem? Is it one time problem or all the chips are having a problem? Now these are all the works that during the testing they will figure it out, and then foundry guys will look at and they correct and they try to improve the yield. So these are all some things. The shift registers are very much used to test whether all the nodes are free from stuck-at faults. Okay, so probably when you read it, when you're in going through the textbooks, you won't know the application why we need this, but that is a reality. So we need the shift register, shifting the data to ensure that the nodes are free from stuck-at faults. So now imagine your input is this and your output is say kind of 10110. Okay, now what does that means is these registers are working as expected. That's a simple thing. That's a simple thing. Clear? So we will need this shift registers. You need to understand shift left, shift right, and all that. Okay, but I would say go and learn about something called scan shift. So modes of operation. So your IC, when you look at your IC, there could be multiple modes. Okay, modes of operations. Okay, one is func mode, and then we have a test. So under the test, you have a scan shift. Okay, and then scan capture. Okay, and then scan at speed. Okay, so these are all your different test modes. Got it? So if you want to explore further, you can actually note this down and then explore it. Okay, moving on to the topics. So shift registers are very very important. This is a concept. Just that you're giving some data and you're checking whether the same data is coming out or not. Now, what does that meaning is if your data is coming out, that means this D and this Q and again this D under this Q, all of them are properly working as per our expectation. Now, this is something would be used at the time of testing. Okay. So, any question in terms of registers? So, try to understand what is the meaning of serial in, serial out, parallel in, serial out, serial in, parallel out, and different things, and shift left, shift right. There is something called the Johnson counter, and different things. Okay. See, it is a more of, see, anything that you learn here, nothing is going to be a waste. It is just that the moment you look at your designs, you can easily understand. You can actually bring up your own GUI and then understand, the schematic part or gate level circuit part, and then you can easily understand the things. Okay,
Sir, I have a question, sir.
go ahead.
Is it okay to call for all the flip-flops as a register in any
Your voice is not clear. I'm sorry, I
process?
cannot hear you. Your voice is not clear.
Yes, sir. All we can call all flip-flops as a registers in our design.
Right.
read
They are basically registers only. See, all the flip flops are called as the registers only because they store the value. No, as simple as that. They store the value.
Just an extended question. So this flip flops will store the value, but actually, is there any uh, corruption which occurs in the flip flops?
No, what is the meaning of corruption occurs in the flip flop?
So if data actually is stored as one, okay,
No,
but actually if the data becomes actually something around like zero or something that
no,
toggles by
no,
itself, like doesn't.
no,
Okay,
no.
that will be always okay, always on. Whatever.
See,
Okay.
it is this flop. The way the flop is designed is it is if it is zero, meaning it will retain that value zero. There is nothing that it will actually look at things.
Irrespective of any time period.
Correct.
Okay. So then, what is the difference between like memory and flop then? So because memory also does the same thing, right?
Okay. So now that is assignment question for you.
Okay. Fine then. Okay, let me talk. Let me explore.
They both do the same thing. It's just that individual, say simple right now. Say for example, okay, let me give you a simple assignment question now. So there is something called a memory that we use. Now, say you have a 32-bit, okay, bus. Now say you can actually see all this 32-bit can be realized using 1-bit register, 1-bit register, okay, or 1-bit flip-flop, okay. And now there is a 32-bit. It can be used kind of 8 cross 4 memory, okay, 8 cross 4 memory, okay. Now in terms of power area, which is going to be the best one, now you guys can work on it. See, you have to store 32-bit value. Now you use 32 registers, individual flip-flops, and then that is one option A. Okay, now you can also use 8 cross 4 memory. Okay, this is also going to store 32-bit value. Now say that is B. Now in terms of area, which is going to be efficient. Okay, I can say like kind of this is your assignment question.
Okay. So in the shift registers you mentioned, right? Like that will be like designed separately to check this testing cases, right? That will be done based on the blocks and all.
No, shift register,
So
whatever that I told scan shift, that would be taken care by the DFT folks. You will not do anything.
okay, okay.
Yeah. Okay, all right. See, these are all things that usually pretty much, in interviews people would ask. Now, you being a designer, okay, now you don't have that memory, but now how do you realize that? So I would go with this value. But now let's say you have area limited, you have an area restriction with respect to your chip. Now I would actually get rid of individual registers and I would go for say this kind of memories, SRAMs. So there is something we call it like kind of SRAMs. That is static random access memories where you will store the values. Okay. Okay. All right. Now, so let's talk about the next topic, which is counters. Okay. Now, counters. So, what is this counters? What is that use of counters? Now, say simple, right? Like you can actually, have something which is kind of counting it. Say, for example, simple, right? Your clock, your regular, time, it is in your hand. You have the watch, wristwatch, or wall clock, or whatever, right? Now, if you have to implement it with a counter, now how do you go about it? So, hutch, okay, and then SS. Now, if you have to implement this with a counter, so what would be the value? How you will look at? So can you design a wall clock using this counters? We can, right? So it's simple, right? Like kind of say what would be the range of this SS? So the first SS would be, what is the range? First SS
0 to 50,
0
59.
to 9, and this guy is going to be 0 to 5. Okay, so this S is going to be, say, kind of, that means what? 0 to 59 is the range that is allowed for this SS. That means this S is going to be allowed 0 to 9, and the moment it reaches 10, it has to become 0, and this has to be increased. Got it? Now, in this case, it is kind of 0 to 5. The moment it becomes like kind of 5, and this becomes like a 9. Now, what is the next thing it has to happen? This has to become 0 0, and this m has to be increasing it to 1, increasing by 1. Agreed? So this is something that we kind of count something, and then we make certain decisions based on it. Okay, so counter is basically used to keep track of time, and then you can say count something that is kind of how many times it has seen and all that. Okay, now so we have a kind of up counter, down counter, and then you do have a synchronous. The way we implement is like kind of you have got synchronous, and then you have got asynchronous, and then decade counter, and then ring counter, Johnson's counter. So uh, all these are all possible different counters. Okay, now let's quickly design a counter. No, how do we design it? Say for example, now let's look at kind of mod 10. Okay, let's design a mod 10 counter. Now how many flops that we need? How many you know registers that we need in case of, if you want to implement mod 10 counter, how many registers that we need? See, we need, it's basically 2 to the power n states. So if you have 3, that means how many states that we can actually calculate? So 2 to the power n. Okay, so that means if it is n equal to 3, that means 2 to the power
8.
3, which is going to be 8. So that means 0 to 7. Okay, anything that you have to go beyond this, you need to increase the number of n, basically the number of bits, which is going to be 4. So 2 to the power 4. Okay, now let's talk about in this case you can actually count 0 to 15. That means total 16 different states. So for our understanding, let's design only 3 bits. Okay, say now you have got kind of qa, qb, let's say kind of say okay, A, B, and Q, C. That's your 3 bits currently, assuming. Say this is 0, 0, 0, 0. Okay, and then you have got 1, 1, 1, 1. Okay, this is your current state. Now this is going to be your next state. Say for example, QA plus 1. Okay, now this is going to be the next state. Say now assuming when it is in 0, 0, 0, the moment you get your pulse, now what is that it has to be? What is that it has to go? What is that it has to go? From 0, 0, 0, it has to go to the next step, which is going to be 1. Okay, now if you ask me here, it's 1, 0, 1, 2. So it is going to be kind of 0 to 7 state. Now when you look at this particular thing here, Now from 0, so assume that your system is at 0. Now the moment you get a pulse, it has to now increase it to 1. Now 1 to 2. Now assume if it is at 4, now you get a 1, you get a pulse. Now it is going to be 5. So something like this, right? So this is your current state. And now the moment you get your pulse, say if your system is in current state of 100, that means 4. Now it has to increase it to 5. Got it? Now in this case, it is going to be kind of 000, and then it will become 1, 001. Now you have to say kind of TA, kind of TB, now TC. What would be your input? Now you try to recollect your the excitation table. Okay, try to recollect your excitation table. We will, let me just bring that excitation table here. Okay. Okay, so look at this particular excitation table. Now see here 0, and it is toggling. It is 1, which is again toggling. So this TC is going to be always, because it is always toggling. So right, looking at this is your current value, and this is going to be your next value. Now that means what? 0 to 1, and then 1 to 0. Now this is the condition here. It is going to be seen as this two thing. Okay. Now what does this meaning is? So this is going to be kind of 1 1 1. All these are going to be 1. Okay, so this is the input of this particular clock, which could actually fetch you this output. Okay, now the next one, see here, this is B. This is again the next state of B. Now 0 0, what is it you want? 0. Now here 0 and 1, that is going to be 1. Now 1 and then 1, got it? Now that is going to be 0.
0.
And then here 1 and 0, this is going to be 1, and then 0 0. So this is going to be, say, something like this. Okay, so now looking at this excitation table, now you are able to come up with the T flip flop, the next input what you should give. Got it? And then now this is going to be kind of say 0 0 0 0 0 0, and only here 0 and 1. Now what does this meaning is? So this is going to be kind of, see, 0, and only in this case it is going to be 1. Now what about this guy? All three are 1 1, and here all three are 1 1, and then last one is 0. So that means this is going to be your. So now if you look at here, we have actually came up with the table where this is your current state. Now if this is your current state, now you get a pulse. Now the system will go to the next state, which is going to be this. Now to get this, what should be your circuit? This is supposed to be your circuit. Now what is that we need to do here? You need to use this and solve. Okay, now it's time for you to use this and solve using the Karnaugh map. Got it? So you have to use this and solve it. Okay, now this is going to be kind of output. Now your values that are going to be kind of a bar, a plus 1, and then this. Now you have to use them and then find the system, that the circuit that would actually work. Now in the end, you will get something like kind of, see, this. See here, something like this kind of circuit that you will get. Now this is what you will actually get it. Okay, QA, QB, and something like this, you will get it. and and finally you will have this input. Okay, now that is nothing but your counter. So this is how we actually design the whole sequential circuits. Now don't look at this only for counter, this can be applied. Okay, now the first step is to come up with this kind of table where you will have your current state, next state, what would be the corresponding input that could actually needs to be applied so that you'll get your system that is working right. All right. So any question here? How do we design a counter and all that?
So here we are using T flip flop. Like why any particular thing?
No, I'm just for taking it for simplicity purpose.
Okay.
Now, simple, right? On a simple note, now let's see if you have to get the T flop, okay, T flip flop using D. So now
Okay.
how it is going to be? Say if this is your T flop,
Then-
okay. Now the simple thing is say this is going to be T now, but you can actually have it like kind of this. See, you can have it like kind of say something like this. That's your D flop, which could be toggling all the time. Say something like this. So these are all some things in a simple note. You can actually convert them and you can use it. You getting it?
Like that means actually giving input for D and taking output at Q bar.
You can
That is
say
D.
that way. No, that is I won't say that way, but there are
Uh-huh.
different ways to take that. You can actually,
Okay.
say that, right? Like design a D flip flop using SR flip flop. In the textbooks, you might have read
Yeah,
all.
yeah, yeah. Correct, correct,
So
correct.
something like that, you can convert
Mhm.
it. See,
Okay.
I'm just trying to show how we can design a system. So it is if you want to design using only D flip flop. Now what you need to do is you can actually use the uh, excitation table of D flip flop and do the whole thing. You understand? Say now, if you want to
Sure.
design using the D flip flop, so you can actually pick this and refer this particular thing when you are actually designing the system. Now, instead of this T, what is that you have to do is it is going to be say kind of DA something like that. Okay, so you can actually refer this. Say
Sure.
for example, now here, see now ideally what I would say, you can just copy all this and put it over here. Got it? Now you need to solve this using the K-map or whatever the method you are comfortable, and then design the system, which could just simple. Your combo logic, it could be kind of see, it would be kind of D flip flop. Say this is going to be say kind of DC, DB, and then say DA, something like this, and then you will have your logic. It could be anything. It could go something like this. Got it? Now, in this case, you have to just use the T flip flop, which could, the logic could be different, as simple as that. You're getting it?
Yeah, Kumar.
See,
Yeah.
you can design using any registers. Only thing is, whatever the register or whatever the flop type that you are choosing, you can actually pick that for your design. You need to
Okay.
use that excitation table, as simple as that.
Sure. Thank you.
Okay? Yeah. Any questions? See, you are not, you see, your goal is not to design this, but you having an idea of this circuit. Now, remember, the reason why I am talking about this is it is something that, you will deal every time register to registers. So, this is ideally, if you ask me, I would say this particular path, I would say there is something called reg to reg path. Now, again, this particular thing, reg to reg path. So, when we do static timing analysis, you have to look at how much time, what is the logic, how much time it takes to travel, and all this it will have to, it matters. Okay, so you may not know the functionality. See, if, because I work in a different design. So, if you ask me, Kumar, do you know what is the function of this particular path or this, logic? I wouldn't know because that is not my work. Okay, so that is actually part of the designers who is coding the RTL. Now your role is optimize, place and route perform the cell placement and optimize them to reach on time. That's a basic thing, as simple as that. So you should look at, every path as a four types. So there are four types of paths that you will actually look at. One is, say, for example, okay, now if you look at this particular thing, say here, assuming this is your whole system, okay, this is your whole system, okay. Now there is an input, there may be a combo logic. Now this is another combo logic, okay. Now there is another combo logic and all. Say now this is going out combo logic. So now ideally, if you look at, say, this particular thing is called input to register, okay. Now this is going to be kind of reg to reg, okay. Now this is going to be kind of, again a reg to reg. Again, this is going to be kind of, reg to reg. Now what about this register to out, okay, register to out. So there are four types of paths that we look at. So when we talk about STA, we will look at in detail. So input to register, okay, and then register to register, and then register to output, okay, and then in to out. So there are four different things that you have to look at. You will be analyzing it when we get into something called STA part. Okay. Any questions? So that is why it is kind of, you may not, you don't need to worry about whether it is a counter or shift registers and all. What matters to you is how many logics that I have here and how they are placed. Is there too much distance? What is the cell delay and what is the net delay? What is the overall delay? So that is what we actually bother. Okay. Okay. So you guys try to understand how this all actually, being designed. You can take one particular scenario and one of the example and try to analyze it and then design it. So that, like, what is the process of designing these circuits. Okay. Okay. And the last topics for the day, I'm not going to spend too much time, but if you look at this, going to be kind of with the state machines. We see these state machines are very much important if you are in the front end, where, when you are designing a circuit, you will come across a lot of state diagrams, and then you have to design the states, whether you want to go for Moore machine or Mealy machine. But PD engineers, it is not at all a big deal, because we don't anyway look at the function of, we look at the functionality, but we don't change any of that. So it is end of the day for me, whatever I said, that is going to be rich to rich path, or, into rich path, and etc. So end of the day, even all these state diagrams and then, state machines and everything will become like kind of circuit, something like this. When you design your thing and when we do synthesis, this is what you actually get. So I have not got it. There was no need for me all these years to know, what kind of state machine it is and all that, because that is not my work. That is actually the front end guys who are actually, designing the circuits. Okay. So I would say, learn the basics of the sequential registers and counters and, different flock types, uh, and state machines. You can just go through a basics and understand what is the meaning of it. That should be good enough, if you are trying to build a career in PD. Okay. So I think that's all I wanted to, cover in whole digital part. So with this, we will wind up the whole digital part. So any questions? So I'm just, you guys might have read all this digital part, looking at the books, and, we might be wondering, okay, what is a circuit and all. But I just try to throw some practical scenarios where it is easy for you to understand. Okay, so that's a difference that I wanted to bring it here, and I hope I have done that. And that is why people ask me, "Kumar, really digital electronics matters for a PD engineers?" My answer is yes. You should know, because okay, now say simple, right? Here, look at here, what type of cell it is. Okay, it is a AND gate. Okay, now what is the delay that it is going to take? So A2, say this is A, this is B, say this is Z. What is the delay it is going to take when it is A to Z signal change? When there is a signal at the A changes, what is that it is going to take? And when there is a B2, when the signal at the B changes, what is the delay it is going to take? Now, what is the size of this cell? Okay, and what is the power that is actually consuming? Is it sitting in the right location? So end of the day, you are actually going to be building a digital chips, and you should know ideally what the cell type is, and what is the function of the cell and all that. Okay, so my answer is yes, you should actually know the basics of digital to be a successful PD engineer. Okay, so that's all for the day. And next week we would be moving into CMOS circuits completely now. So you are looking at all this in terms of gates, correct? Now, whatever that you are looking at all this in terms of gates, now we will try to understand now how these gates are designed. What is the best way? How your gate delays, and all that. What is the area? How this gate area is determined, and all that. So now that is going to be your CMOS. Okay, so that is going to be the next couple of weeks. We will be looking at CMOS basics, and then we will be getting started, on the real part. Because without these two, I don't think you would be able to learn PD and do PD. Okay. All right, that's all for the day, guys. I think I'm done.